Okay, allow me to start because there's a lot of things to say and there's only so little time. We are going to talk about coroutines. Who has attended the conference last year and as I was there to for my other talk about coroutines? Oh, yes, a few. Now this time is different. We are going to see actual code. Thanks to the sponsors and the location and the staff for the conference. For those who don't know me, I am a C++ programmer since 1990. I work in the video game industry, and currently I am a co-trainer of game programming at the Digital Bros Game Academy. And I follow the work of the C++ committee since 2018. And what will we see today? We will see a skeleton implementation of a very, very simple coroutine framework. The C++ coroutines, which have been integrated into the C++20 draft, are almost final, but there are just a bunch of extension points. We are a programmer, we need to write types that make coroutine happen, so we will see how it is done. We will see a very simple application of this framework for inter-process communication. A few parts are Windows specific. I'm sorry for people who prefer other OSs, but it's very easy to adapt the codes for other systems. It is written with Visual Studio 2019 with /std C++ latest and /await. This is essential. There is no user interface to set this switch on the on the command line of the compiler, so you have to add it manually in order to compile the coroutine codes. Okay, everyone is comfortable with the concept of coroutine? Who has never heard about coroutines yet? Oh, only one. Okay. Briefly, a coroutine is a function that can be suspended in the middle and then resumed at the point where it was suspended. We will see example very soon. While the coroutine is suspended, it's not like a blocking call. The thread actually is not stopped, but execution flows to another coroutine or another function. This allows us to create a situation when we can write easily cooperative multitasking codes using coroutines in a single thread, and that's what we are going to do. This is the final goal of this talk. We are going to write, we said, inter-process communication. So we have a server and a client, and we create a named pipe between the two processes, and we pass some data from the server to the client. In this case, the server coroutine creates a pipe, awaits until until a client connects to the pipe. So this is a asynchronous operation. When the client connects to the pipes, we get the pipe. We create some data in some way, it's not specified, and we write the data onto the pipe, and we wait for the success of the operation. While we are waiting for the create pipe, the compiler can execute some other code, some other coroutine that has been scheduled in our system. On the server side, it's practically the same. We open the pipe, we await until the pipe is connected with the server. We create a buffer and we read the data from the buffer, from the pipe into this buffer. We get the length of the data that has been read, and we do something with the message. So this is our final goal. There is a lot of things to do to get there, but it's not conceptually very complicated. So we see in these two examples a couple of reasons why should a coroutine suspend. The coroutine suspends basically for two reasons. We suspend because we wait for another coroutine to complete, or we wait for an asynchronous operation to complete. This open pipe here and this pipe read here are coroutines themselves. So this core waits is launching this coroutine and then waits for the coroutine to complete. What is not shown here is the second case, waiting for an asynchronous operation. What does it mean? Because to create the pipe, to write on the pipe, these are operating systems calls. We are not going to use blocking calls. We are going to use non-blocking calls. And then the operating system will start the operation in the background, probably in another thread. We don't care about that. But at some time, the operating system notifies us that the operation has completed. And at that time, we want to resume the coroutine. Since we are focusing for this talk on Windows, the second case can be written like this. On Windows, most of the asynchronous operations are managed through this handle object there. So waiting for an asynchronous operation to complete is essentially waiting for a handle object to become signaled. Let's see. Let's write this framework that does these two stuff. First of all, we need to create some mechanism to schedule the coroutine and let them happen. We just use the classic pattern to have an event loop. I called it coro loop because launches coroutine. So our main function is just create the coro loop, add some coroutines to the loop, and then calls loop run. The loop will have a pool of coroutines, and it chooses a coroutine that is ready to be executed and launches it until its suspension point, and when it reaches its suspension point, it puts it back into the pool. And then until we have coroutines to execute. What does the language give us to implement this kind of stuff? The main ingredient is this template here, coroutine handle. It's in C++20 will be in STD in the STD namespace. In Visual Studio, it's still in the STD experimental namespace. This is class template. The type, we will see what the type means in a few slides. What we need to know at the moment is that the coroutine handle void, or simply without the type, which is, since void is the default type here, can represent any kind of coroutine. If we specify a type here, then we are tying ourselves to a specific kind of coroutines. We will use both. The interesting part is that coroutine handle T is always convertible to coroutine handle void. So, so this is actually the most generic way to refer to a coroutine. So how do we write the coro loop class? It's actually very easy. It has a bunch of vectors that hold coroutine handles. And a few functions. We see a function one at a time. We have the default constructor. We use a singleton pattern here. It's not necessary. It's not, the framework is not tied to the singleton pattern, but it simplifies the code in a few places. Anyway, it's a single thread application, and the coroutine, the coro loop is instantiated only once in main, so there are no dependency issues or order of the initialization issues. Okay, now we have two, remember we have two use cases. The blocked function handles, the coroutines that are blocked waiting for a handle to become signaled. So we have this schedule blocked function here. Okay, this function is scheduled to say that this coroutine is blocked by this handle. And we simply add the handle to this vector and this coroutine handle to this other vector. And we keep the two handles there. And we also have a ready coroutine part. This will be used to handle the other case when a coroutine waits for another coroutine. We simply add this coroutine handle to this vector. So this vector contains coroutines that are ready to be executed, while the other one contains coroutines that are blocked, waiting for a handle, for a specific handle to become signaled. Okay, so now we come to the coroutine loop, coroutine loop run function, which is more interesting. It's a loop, so it starts with a while. The loop is executed until we have at least a coroutine to work on. Until we have at least one empty and at least one ready. Oh, it should be an or there, not end. Okay, and then we go with processing the blocked coroutine and then processing the ready coroutines. Let's see the first one. The first one, processing the blocked coroutine. We use this Windows function. This function waits for a set of handles and check if any of them become signaled. So we pass the vector of the handles, the handles, the big handles. And this function is potentially blocking. It blocks for this timeout here. The timeout can be infinite or 0 or any other time, but we use only infinite and 0. Why do we use this? Because if I do not have any ready coroutine, that it doesn't make any sense to exit from this function unless at least one of the handles becomes signaled. So we just pass infinite. On the other hand, if I have a ready coroutine, I pass 0 as a timeout, so that the function just checks if any of the handles has become signaled in this moment. If no handle has become signaled, then we go further and try to execute the ready coroutines. If this function returns because one of the handles has become signaled, then the result is in this range. And what do? We just compute the index, and then we remove both the handles and the coroutine handles from the respective vector, and then we call this coroResume. Resume is a function of the coroutine handle template that does the magic, that gives a control to the coroutine. What does it do? Really, it jumps into the coroutine in the point where it is suspended. The coroutine is executed. Eventually, it reaches a suspension point. When the suspension point is reached, the flows returns to resume function as if the resume function returns. And so the control gets back to the coroutine loop. The last part, how do we resume a ready coroutine function, is very easy. We just iterate on the vector and call resume on all the coroutines. We make a copy just to avoid maybe while resuming some of this coroutine, they may need to modify mReady. So we avoid modifying the vector while we are iterating. Okay, so we already saw an example of coroutine. This is the client we already seen before. We can see also this pipe here. It's written like this. This is coroutine which takes the name, creates a pipe, core waits until it's connected to the server. We will see the full code at the end of the talk. And then this core return here prepare the pipes that is returned to the caller. The interesting part is the role of the template type here. This coroutine, without argument, the type is void for default because it doesn't return anything. And this one instead returns this pipe here. And so we have to write the type here. So we see coroutine have this strange ambiguity because they look like a function that returns a coroutine pipe, but they actually are a function that returns something else with this co-return here. Except for any one of you has ever worked with Future, std Future from the standard library? Okay, the idea is very similar to the standard Future. This is like a function that returns a future pipe, and we will see that we achieve that using the same pattern as the standard Future. Okay, the interesting part of the coroutine is what makes this function a coroutine. It is not this type, but it is this keyword. A coroutine becomes a coroutine when the compiler sees either co-await or co-return or co-yield into the body of the function. So it's the presence of this keyword here that starts the coroutine transformation. The compiler, when it sees co-await, transforms this body into a factory of coroutine objects. And let's see what is a co-await expression. First of all, it's an expression, it's not a statement, so it has a value. In fact, we used the value before to assign to a variable. Of course, it introduces a potential suspension point. The name says, okay, I'm awaiting, so I'm suspending until something happens. And what does the compiler do when it sees this? First of all, it evaluates the expression, and let's call the expression E. By calling methods on E, the compiler generates the custom code that will implement our coroutine framework. We will see in a few slides, there are 3 special functions that the type of E must support. And if E has all these required methods, we call that the type is awaitable. You may have seen a little iceberg here because I'm not telling the whole truth. There are a few steps between this bullet and this bullet that I'm not talking about, but I'm trying to prevent you from information overload. If you want the whole story, just have a look at the standard or at the presentation I did last year. Okay. Suspending. The compiler has evaluated the expression and then checks if we need to suspend. First of all, the compiler calls e.awaitReady. This is the first function that E must support. This function should return a boolean. And if the result is true, E is considered to be ready. And if it's ready, there's no need to suspend at all. So if await ready returns true, the coroutine is not suspended and simply continues. If await ready returns false, then the coroutine must be suspended. And the compiler calls e.awaitSuspendH, where H is a handle to the coroutine that is being suspended. And this is the main point that we need to be implemented. Because here we need to do something non-trivial to make all the machinery work. There's another iceberg here because I'm missing a few details, but allow me to go without that. Okay, resuming. Eventually, the coroutine will be resumed. So the control flows back into the coroutine that is still awaiting for the result. We are not finished with the await expression because we said that as an expression it has a value. So the compiler calls e.awaitResume to compute the value and possibly do something else. But usually the responsibility of this function is to compute the value of the await expression. This awaitResume may be void if there's no such value. Okay, that's enough for the theory. Let's write our first awaitable type so that we can see finally some code. Let's write this type that is able to make a coroutine suspend and wait for a handle to become signaled. We write this handle class. This is only a RAII wrapper around the handle object. Let's give it a constructor, destructor. Let's make it movable but not copyable, so it has the right semantic. If we move and we avoid closing the handle twice. And these three functions are the one that makes this type awaitable. Okay, so let's implement these three functions. Await ready, it's easy, returns false. There's no way in Windows, at least, to know in advance if a handle is already signaled. The only way to check if a handle is signaled is to wait for it. So we just return false. Okay, we don't know, so we assume that it is not ready. And what we do we do when we suspend? We just schedule the coroutine in the coro loop. That's it. That's it. The coroutine is suspended, but the handle to the coroutine that is being suspended is given to the coroutine loop and saying that it is blocked by this handle. And the code that we see before in the coro loop will resume the coroutine only when the handle becomes signaled. The last thing to do is to resume. In this case, co-awaiting on a handle doesn't give us any information, so we don't need the co-await expression to have any value, and so we have this awaitResume function that returns void. So with these three little functions, we make this handle class awaitable, and you just can write co-awaits with the handle, and it does all the magic. The coroutine is suspended and is scheduled, and when the event becomes signaled, the coroutine is resumed. That's nice. So now we have to write this coroutine type here. The coroutine type, we always see that we have a template argument which will hold the result that we are going to pass out of the coroutine. I like to use the no discard attribute on all my coroutine types. It helps find some nasty bugs, so I encourage you to do so. Usually because since a coroutine object is returned from a coroutine function, it is usually an error to discard the return value. Okay, I mentioned before the STD future. STD future, if you know the pattern, work together with an object that is called STD promise. And it's not a coincidence that we use the same term here. When the compiler compiles a coroutine, the first operation that it does is to select the promise type. By default, the promise type, if C is the return type of the coroutine, then the promise type is C::: promise type. This selection can be customized, especially in this template, but I leave it into the iceberg to the specification of this. So let's write it simple. Our coroutine here needs a promise, and we use these to hook the promise into the coroutine. So when the compiler sees a coroutine, it sees that it returns a coroutine object. It checks this type here, and it knows that, oh, the promise is this type here. This object will be used by the user of the coroutine. This one is actually an implementation detail. It shouldn't be, it doesn't need to be exposed to the user. Okay, what does it happen now? We have selected the coroutine. The compiler allocates what is called the coroutine frame. The coroutine frame, the frame of the coroutine can't be allocated on the stack, because otherwise it would be impossible to suspend and resume because of how the stack works. So the coroutine must be allocated somewhere else. The coroutine frame, what does it contain? It contains all local variables, including the function parameters, an object of the promise type that we selected in the previous slide, and some other implementation stuff that we are not interested. By default, the memory is allocated on the heap using the global operator new. The allocation can be customized, but there's another iceberg here. I'm not going into the details. Okay, let's visualize what is happening. We have the coroutine here, we have the caller function here, and we have heap memory here. The coroutine creates the coroutine frame that is able to store parameters, the promise, and all the local variables. First of all, the parameters are copied. The parameters of the function are copied into the frame. We are not going to use the original parameters. From now on, we are using this one. Then we construct an instance of the promise type that we selected before. And now the promise type creates the coroutine object. This is, as I said, it's similar to the future promise pattern of STD future. So it's the responsibility of the promise that is created into the asynchronous function to create the future object. In this case, the coroutine object. The coroutine object is created directly in the context of the caller function, because here we are exploiting return value optimization to do so. Okay, so how does the promise create the coroutine object? It's very simple. If P is the promise object, then the compiler calls P get return object. So the promise type must implement this function. And so what does, and we'll see in a few slides how we should implement it. We started by introducing this coroutine handle, but I didn't tell you what is the type of the template. The type of the template is the type of the promise. The coroutine handle promise, if we specify promise as the template argument, we make it possible to pass from the promise to the handle and vice versa. So there is a one-one relationship between the promise and its handle. Okay, so since we want the coroutine object to interact with the promise at a certain point, we want the coroutine object to store an object of this type, coroutine handle promise. We use the promise so that the coroutine object knows the kind of promise that he is referring to. So let's write the code for this. We just add this coroutine handle promise member here, and we create a constructor so that the coroutine can implement, initialize the coroutine, the mcoro member. And then the coroutine get return object in the promise. What does it do? It simply creates a coroutine result object by passing this expression. This from promise is a static member function of coroutine handle promise that does the conversion from promise to coroutine handle. Okay, so we allocated the frame, we initialized the variables, we created the promise created the return object. Now, finally, it's the time to enter the function body. We didn't enter the function body yet. The function body is wrapped into these codes. In fact, the compiler adds what is called an initial suspend point here, and appends a final suspend point here, and then wraps the whole body into a try-catch to avoid exception to escape from the body. For time reason, I'm not going to describe the exception part. It's quite easy. You can check which you can check in the, on the standard library, or you can see the slides from my previous talk about this. But let's focus on the two suspend points, which are interesting. The first interesting part is that they are implemented with the normal core await. So the function called just one entry point here, and it expects this function to return an awaitable type. And we see what an awaitable type here is a type that has await ready, await resume, await suspend, await resume. And we are doing twice, one here and one here. Okay, so what should we do in the initial suspend point? Actually, in our case, we need to do nothing. We don't want to suspend at all, so we just return this type here, std suspend never. This is one of the two trivial awaitable types defined in the library. It's just an awaitable types that whose await ready function always return true. So it's always ready, it never suspend. The other trivial awaitable types is suspend always, which always suspend. So our coroutine will not suspend at the initial suspend point. When called, the execution enters the body and runs until there is another suspension point. And the final suspension point is more interesting, and actually is a bit more complicated because it's here that we need to manage the other case, which is the case where a coroutine awaits another coroutine. We need a little some other things to do. What the effect is that two things should happen. We have to compute a value in the coroutine and give it to the awaiting coroutine, and then resume the awaiting coroutine that is suspended on the core await expression. So these two things should happen. Let's see, this is a reminder. So we have this function here. This is calling another coroutine and awaiting on the coroutine object that this coroutine is returning. This is a coroutine that is being called and that has this core return here. So the final suspension point, which happens here, needs to do what? Move this pipe here and then resume the other coroutine that is being suspended. These two tasks. Okay, the first thing to do, since we are applying core await on this, which is a coroutine pipe, we need to make coroutine awaitable. So we need to give coroutine the three magic functions. So we need to make awaitable. We use await ready, and what does we do? This time we don't return neither false nor true. We use this done, the done function on the coroutine handle. Just check if the coroutine has already completed. If the coroutine has completed, then the result has already been computed, so there's no point in awaiting. Otherwise, if the coroutine is not done, then we need to wait. And what do we do if we wait? Okay, if we wait, the await suspend is called with the handle of the coroutine that is being suspended. And what do? We just say to the promise or the other coroutine that, oh, I'm awaiting on you. So we store in the promise of the second coroutine the handle of the suspended coroutine. We need to add this member to the promise to do so. We will need this coroutine handle so that the promise will resume the coroutine that is awaiting. Okay, now how do we compute the return value for the coroutine? Let's see with this animation. The coroutine computes the result, and then the first step is to move the result into the promise. And this step is performed by the co-return statement. The co-return statement should have this effect. The co-return statement, like a normal return statement, has two forms. It has a form with an expression or without an expression. And implicitly, if the execution flows off the coroutine body, there's always a co-return without expression. Okay, in this case, the co-return is implemented by calling this. P is always the promise object, and we call return value with this expression. In the other case, we call return void. The problem is, what is the problem? The problem is that the promise type has to either implement this or this. It can't implement both. Otherwise, we will have a compiler error. And what is the best thing to get this one or this one? If we had concept, we could do it better. Now we just use a partial specialization of templates. Instead of specializing the entire promise class, I prefer to have this basic promise type here and specialize this and let an unspecialized promise type to derive from the basic promise. And the basic promise is like this. For a generic result type, we store an optional result, and then we implement the return value here and by moving the value into the result. Easy. And we just give an accessor here to let the promise extract the result. We specialize this template for void, and for void it's very simple. We just have return void and the result returns void. For a better result, we could also have a specialization for reference types, since we can't have optional references, but that's an exercise, it's very easy. Okay, so we stored the result into the coroutine frame. Now the next step is to move the result out of the coroutine frame into the caller. And how do we do this? We already mentioned how it is done before. It is done by the await resume function. So the await resume function of the coroutine, of the coroutine result type, just get the promise. This is another method of the coroutine handle that gives me the promise given a handle, and I call the result that we just implemented to extract the value from the result and return it to the caller. Remember that this the result of this await resume is used as the value of the core await expression. Okay. Finally, we can implement the final suspension point that we left open. We need to resume the awaiting coroutine. The task is not trivial, so we would need to invent a new awaitable type because the final suspend function should return an awaitable type. Actually, I like a little trick here. Instead of creating a new type, I just make promise awaitable and return a reference to the promise. So I put the await ready, resume, and suspend directly on the promise. I return a reference because I want to avoid copies of the promise object. And then we have the three functions, await ready. Await ready must return false. This is important. We must stop at the final suspension point. Why we don't want to, we need to stop at the final suspension point? Because if we don't, the execution will flow off the coroutine, and if the execution flows off the coroutine frame will be destroyed by the compiler. And if we destroy the coroutine frame, then the caller can't access the return value, which is still stored in the coroutine frame. So in order to give time for the caller to get the return value, we need to stop here. And the await suspend, what does it do? Remember, the last task we do is to schedule the coroutine that is awaiting for us. If there's a coroutine awaiting for us, then we just schedule as ready into the coroutine loop. And then the coroutine loop will resume the coroutine at the next iteration. Why do we need to get to the loop? Because we can't call resume into this function. Bad things will happen, trust me. If you want to know more, you can ask me later. But we can't resume the function directly here. We need to happen outside of this function. Actually, the need to resume the coroutine here has been heard at some level. So in C++20, this is not yet implemented in Visual Studio, but we will be able to actually return the coroutine handle of the coroutine that we want to resume. So this will avoid passing through the coroutine loop. It's much more efficient. Okay, the last function on the promise is the await resume. This will never be invoked because it is undefined behavior to resume a coroutine that is suspended on the final suspension point. So we leave it empty. Okay, so there's one last thing to do. I said that we stopped at the final suspension point because otherwise the coroutine frame would have been destroyed too soon. But now no one is destroying the coroutine frame. So we need to destroy the coroutine frame. And where is the best place to do it? It is in the destructor of the coroutine object. So the coroutine object, which lives in the caller, has extracted the value, and now that it has extracted the value, it can it destroys the object and it destroys the coroutine frame. And that's it. We're almost finished. This is all our machinery. On this machinery, we can write finally the code that I promised you in the beginning. Let's go it. I've been only 5 minutes, so I'm going very, very quickly. Let's write. We can write a pipe class, or it's also another AI wrapper around another handle with constructor, destructor, move only constructor, etc., etc. And we have these three functions: one to create a pipe, to open the pipe, to read, to write. And let's see. I hope that you can read because it's quite a little, very small font. But we create the name pipe here by passing this flag overlapped so that we create it in the non-blocking mode. Then we create a handle, and we see this is the very first awaitable class that we saw in the presentation by calling this create event. We store this handle in this overlapped structure. With this is only because this function requires a pointer to this structure here. It doesn't do anything fancy here. And we call this connect name pipe. This function is asynchronous, non-blocking. And it returns immediately and checking the error, we see what has happened. If the error is pipe connected, the pipe has been connected successfully, and there's no need to wait. If there is an error, we have an error. An error will be reported in some way. Let's assume that this function doesn't return. Otherwise, we need to wait, and we just say wait event. Event is awaitable and does all the magic. In these cases, in these cases, the pipe is properly connected, and we just return it to the caller. The open pipe function is similar. Unfortunately, there is no non-blocking function to perform the operation on the client side, so we do the hard way. We just create the pipe with open existing, so hoping that a server has created it for us. And if there is no, if we found the pipe, we return it. Otherwise, we check. If the error is not found, we just wait a second and try again. And look at this, wait for 1 second. This is just an awaitable type that you can very easily write using the machinery that we saw by using a waitable timer. You call the create waitable timer function from Windows that returns a handle that you can await. So that is really 2 lines of code to write this. We just see the read function is very easy. It's actually similar to the one before. We create an event. We wrap it into this overlapped function. We use this read file, which is non-blocking. And if it returns 0, then it has already it has executed synchronously. Otherwise, or there is an error, or we have to wait because the operation is pending. And we just say co-await here. Then we call this function to get the number of bytes read and return the number of bytes read. Very last slide. Bootstrapping. We started from this slide, but I didn't write what should I write here, and this is what I write here. This is the server side, of course. This creates the coroutine, starts executing the coroutine, reaches the suspension point, then returns here, store the coroutine handle, the coroutine object into this coro object, and then runs the loop. I need to store the result into this object here in order to let the object be destroyed after returning from run. Otherwise, the coroutine would be destroyed before entering the run. And thanks for your attention. Just one more thing. Source code for all you've seen in the presentation can be found here. Actually, you find a little more code here with the exception handling and some other stuff. It's described here what is the differences. If there are any questions. Then, is there a microphone for... C'è un microfono? No. Ah, questo. Hopla. Oh.
No?
No, it's not working. Okay, I repeat the question.
What was Windows specific? Wait for multiple object and a pipe. Was it right?
Yes. Yes.
The other stuff could be done with other predictions.
Yes. The question was what was the Windows specific part? Is actually they wait for multiple objects and the handle part. Yes. If you replace the handler class with another class and wait for multiple object X with anything that can wait. Select, exactly, yes. You can keep this code like this, and it will work with other operating systems. Actually, the framework, you see that how it is specified in the C++ language is very flexible. You can do actually whatever you want. You just, the compiler calls entry points and you just implement it and make whatever you do, whatever you want happen. Other questions?
Last question. Time for only one.
Okay.
No one?
No questions? Thank you.
Don't be scared.
Thank you again.